Let us discuss this theorem. So in this theorem, we have a matrix space XD. We have a subset A of X. So what we have to prove, P is a limit point of A if and only if there exists a sequence of distinct points of A converging to P. I will draw a diagram so you can easily understand what I want to say. So see, suppose this is a matrix space XD. Okay, so this is matrix space XD. We have some subset A of X and P is a limit point of A. Okay, I will write here. P is a limit point of A. If and only if there exists a sequence of points of A, okay, distinct points of A converging to P. This thing we have to prove. If and only if part is there, so we have to prove in both ways. So here I am assuming first P is a limit point of A and we have to find a sequence of distinct points of A which is converging to point P. Let us start with this assumption P is a limit point of A. You are familiar with the definition of limit points, so I am going to use that. So therefore, for every r greater than 0, BPR minus singleton P intersection A is not equal to phi. So this is definition of limit point and it is true for every r greater than 0. So initially I assume r is equal to 1. Putting r is equal to 1 in star. So what will I get if I put r is equal to 1? We will have B P1 minus singleton P intersection A is not equal to phi. That means if you draw a ball around point P with radius 1, okay, it intersects A. Okay, that ball minus singleton P intersects A. So definitely we can find one point from that set. Therefore, we can choose, okay, we can choose one point. X1 belongs to BP1 minus singleton P intersection A. I am selecting one point X1 from this set, from the intersection. After that, what will I do? I am going to put r is equal to 1 by 2 here. Let us write remaining part here. Putting r is equal to 1 by 2 in star. See, if I put r is equal to 1 by 2 here, what will happen? We will have B P comma 1 by 2 minus singleton P intersection A is not equal to phi. That means this time I am reducing the radius. I am taking half, okay, half radius. So see, we will have a circle like this. So again we have this ball intersect set A again. So again we can find some point from the intersection. So therefore we can choose x2 belongs to BP1 by 2 minus singleton P intersection A. So we have taken one point x2 from the intersection again. See, there is no more space, so make a screenshot of it, then we will go further. One thing I should add here, that point x2 should be different from x1. Okay, so after that I will repeat the procedure for r is equal to 1 by 3. That means what I am doing, I am reducing the radius. This time we will have radius r is equal to 1 by 3. Then again we can find some point x3 which is other than x1, x2 and which lies in the intersection. Since each time we are getting intersection not equal to phi. So in general I will put r is equal to 1 by m. So we will have circles, okay, concentric circles having center P and radius is reducing here, okay. So see, after that what will happen, again for r is equal to 1 by n also we will have intersection not equal to phi. So again we can choose one point xn. So therefore we can choose xn belongs to ball BP1 by n minus singleton P intersection A, and I should mention other than x1, x2 and so on xn minus 1 and so on. Okay, and so on. That means we will continue this procedure. Okay, and so on. So that means we can repeat the same procedure infinitely many times. Okay, so what we are getting, each time we are selecting point x1, x2, x3, x4, x5, xn and so on. That means we are getting a sequence. We are getting sequence, and the speciality of this sequence is that sequence, all points of a sequence lie in this intersection. That means all elements of sequence are members of A. We are taking points from set A. So, and all points are distinct since no other point is same as the previous one. Okay, so therefore I can write. So therefore we get a sequence xn of points of A, sequence of, I should write distinct points of A. Okay, of distinct points of A such that xn belongs to B P comma 1 by n minus singleton p also we can write, but it's okay. So xn belongs to this open ball. Okay, so yeah, the x1 lies in first open ball, x2 lies in second open ball. So xn belongs to this open ball having center p and radius 1 by n. Okay, so now I am going to prove this sequence xn converges to p. Using definition we have to prove this thing. Okay, so see, xn lies in this ball, therefore distance of xn from center of ball is less than its radius 1 by. So this is a very important thing we have got. So I will call it as inequality number 1. So using definition we have to prove the sequence xn converges to p. Epsilon definition. So for that purpose I am taking one epsilon. Let epsilon greater than 0 be given. I hope you remember Archimedean property. Archimedean property I am going to use. So by Archimedean property, what can we write? Archimedean properties say there exists a natural number greater than any given real number. So therefore, there exists, I can write a natural number such that 1 upon epsilon less than capital N. That means we can find a natural number greater than 1 upon epsilon. I will simply interchange them. So what will happen? 1 upon N less than epsilon. This is inequality number 2. Okay, so yes, there is no more space, so make a screenshot of it, then we will go further. I kept these two inequalities here. Okay, so see, after that what will I do? For n greater than or equal to capital N, right? So if you take reciprocals of both sides, inequality will get changed. So therefore 1 by n less than or equal to 1 by capital N. This is inequality number 3. So now from 1, 2 and 3. Can you tell me what can we write from 1, 2 and 3? Yeah, I will start from there. So d of xn p. So we have got there, this is less than 1 upon n. 1 upon n is less than or equal to 1 upon capital N, and 1 upon capital N is less than epsilon. A less than b, b less than c, c less than d. So that's why we can write a less than d. So therefore, by using this thing, this is less than epsilon for all n greater than or equal to capital N. I should carry this condition. So this is definition of convergent sequence. So therefore, what can I write? Therefore, sequence xn converges to p. So here xn is the sequence of distinct points of A which is converging to p. So I should mention here, it is not required. Let me remove this part. Okay. So therefore we have a sequence xn of distinct points of A converging to P. So in this way we proved half part of this theorem. After that we have to assume this thing. That means we have to assume there is a sequence of points of A, distinct points of A converging to P, and then we have to prove that yes, P is a limit point of A. We'll go for the remaining half part, make a screenshot of it first. See, conversely, we assume there exists a sequence of distinct points of A, xn, and which converges to P. We have to prove that P is a limit point. Okay, so let us start with a definition. I will go with a definition. See, therefore, xn converges to P. Therefore, for given epsilon greater than 0, instead of epsilon, I will take r. Given r greater than 0, there exists n belongs to set of natural number such that we are familiar with definition of convergent sequence xn comma p less than r for all n greater than or equal to capital N. Instead of epsilon, I have taken r. So distance of xn from p is less than r. That means xn belongs to this ball with center p radius r for all n greater than or equal to capital N. See, but basically xn is a sequence of points of A. I should mention here, but xn belongs to A for all natural numbers. Getting? See, here we say xn belongs to this ball with this condition, and here we say xn belongs to A for all n. Getting? So that means definitely xn lies in intersection also, but with this condition. Okay, so therefore xn belongs to BPR intersection A for all n greater than or equal to capital N. See, actually every sequence has infinite terms, so there are infinite terms which lie in an intersection, as well as xn is a sequence of distinct points. Getting? So therefore, if you remove singleton P, then also there will be infinitely many terms. So therefore, directly I can write, therefore, what can we write? BPR minus singleton P intersection A is not equal to phi, since many terms are there. Many terms lie in an intersection. So if you remove a single point, then also intersection will be not equal to phi, and this is nothing but definition of limit point. So therefore we can say, therefore P is a limit point of A. P is a limit point of A. So in this way we completed this proof. Make a screenshot of it. After that we will stop. Thank you. Bye bye.